Hello and welcome to the St. Louis Online. I'm Pete Smith, co-chairman of the 40th National Narrow Gauge Convention Planning Committee. The video you are about to watch is part of a series of clinics and layout tours presented as a virtual but slimmed down version of our narrow gauge convention, which had to be canceled due to the coronavirus. We thank all of our presenters for their support and for allowing us to share their work with you. Our thanks also to Russ Segner, Robin Peel, and Burr Stewart for producing this series. For more information on this video and others, go to our website at 40NNGC.com. We hope you enjoy the program that follows.
Excellent clinic so far. We found out what to build and how to put the scenery around it. Now we're going to talk about how to light it. Gerry Cornwell is actually a professional lighting designer. So he's going to help us understand how to properly show off what we've built and at the same time protect the eyes of our viewers. So Gerry, are you here?
Well, thanks to the guys for making all this possible. We go to conventions I find to be inspired, and I always come back from the narrow gauge convention with all kinds of fantastic ideas. And this morning, I didn't have to spend 2 days driving to St. Louis, and I'm already got to redo my scenery and most of my operation plan for my layout. So it's fantastic. Thank you so much to Dean and Guy for taking the time. We're going to talk about layout lighting today. I'm a 40-year experienced lighting designer, and I've worked in commercial and institutional and sports lighting and all kinds of other aspects, restaurants and all kinds of things. But my specialty is museums and art galleries, and that's really where my approach to modeling comes from, is the idea of creating a world, creating a different reality. I've been a lifelong modeler, followed the usual path, and until 2017, I was owner of Mount Albert Scale Lumber Company, and I sold it then to Fast Tracks Hobby Works, and I'm still involved doing marketing and kit design services for Mount Albert. So today we're going to talk about light and color. We're going to talk about the hardware, and we're also going to talk about some lighting design approaches which you may find helpful. So what is it? So light is radiant energy which enables us to see. So we're doing real basics here because I really want you to understand why we see the way we do and what we do to the way we design our lighting in order to accommodate the strengths and weaknesses of our vision system. So radiant energy is what basically enables us to see. And of course, this is human-centric. Obviously, there are other critters on this planet that see differently than we do. Most of the insects see in the ultraviolet, for example. Dogs don't see color. So color vision is very human-centric. Visible spectrum is this very narrow band in the electromagnetic spectrum, and starting from the far left to get all these things that are really bad for us, cosmic rays and gamma rays, etc. And then we get into the ultraviolet, and then the visible range, which is a very, very narrow band. It goes from blue up to red, and typically around 380 to 770 nanometers. And then beyond that's the infrared and all the long wavelength stuff. Okay, the first important concept to get is that is the concept of whiteness, and that is that the color appearance of objects depends on the colors present in the light source. This is not a problem outside, but it's a real problem inside. In spite of what the marketing department of the light fixture might want you to believe, or the light source manufacturer may want you to believe, there is no such thing as a replacement for natural light. There's actually a fluorescent lamp called daylight, and they should have called it Ethel or something like that because it has no relationship whatsoever to daylight. In order to see color in an object, that color must be emitted from the light source. So if you've got a primarily warm colored layout, the colors that we saw in Guy's layout in his photographs, a lot of warm colors. So if you were using, say, a cool white, 4100 to 5000 Kelvin light source, those colors would be lost. So it's really important to understand what are we lighting, and then that'll help us determine the best way to light it. So each light source emits a specific spectrum, And then each object has a specific spectral response. And the perception problems that we have occur when those spectra differ. So when we get a conflict between what we're lighting and how we're lighting it, that means we have difficulty seeing. So let's take a look at some of these spectra and see what they look like. So here's noontime sunlight. Now, you might think this is a bit weird. You would think that sunlight would have a very even continuous spectrum, and as it turns out, it's very bumpy. And that's because we have an atmosphere, and there's all kinds of junk in the atmosphere, which disrupts the wavelengths of light coming through. It's one of the reasons why the sky looks blue. The sky isn't actually blue. Space isn't blue. We perceive it as blue because the light gets scattered as it comes through our atmosphere. And you can see the noontime sunlight is pretty uneven, weak at the blue end of the spectrum, somewhat surprisingly, strong through the center, and it sort of tapers off at the red end. So what is this diagram? So it represents the relative energy at all points on the spectrum of visible light, and it makes it possible for engineers like me to determine the spectrum of source. What's it going to look like when we put it into our environment? It depends primarily on the gas mix in the bulb and the phosphor coating. With fluorescent sources and with many arc sources, it's phosphor coating on the inside of the lamp, which makes the lamp look white when it's off, and that determines the color output of the light, the spectrum. The same problem applies to LEDs. They use phosphors to change the spectral output and therefore the color, and we'll talk about that more shortly. So here's our dear friend, the incandescent lamp. Been around for more than 100 years. And as you can see, it's got a very even spectrum, but it's very poorly distributed. So we have virtually no output at the blue end of the spectrum and all kinds of strength at the red end of the spectrum. And of course, if we had the non-visible part of the spectrum going into the infrared, that's where you'd see all the energy, because this light turns about 15% of its energy into visible light and about 80% of it into heat. It's sort of like a screen door on a submarine. If you were trying to introduce this product today, people would laugh you out of town. Now here's a fluorescent light source. This is a 4100 Kelvin, also known as a cool white fluorescent source. And all arc sources, fluorescent lamps and metal halide lamps have very uneven spectra. They are non-continuous, and the reason for that is the phosphors that are used on the inside will determine where the color is, or what the color is. And we can change this. We can turn this into a 3000 Kelvin lamp by changing the phosphor mix on the inside of the lamp. The basic lamp is the same. It's just an ultraviolet energy source. So if you look at this particular curve, you'll see that we've got a big spike in the blue end of the spectrum and a smaller one in the green and a little bit towards the yellow, and virtually nothing at the red end of the spectrum. Now, if you were to look at this chart and you say, okay, where's my red boxcar going to sit in here? Well, it's going to be towards the right end of this diagram. And as you can see, there's virtually no light output at that end of the output of this particular lamp. So that means that that red color is not going to render properly. You're not going to see that properly. What your brain will do, it'll take the information that it's got coming from your eyes into the visual cortex. It'll take a look at it and go, what do I make of this? Well, I think it's kind of brown. So your brain will interpret this information as a muddy sort of color. So you will not be seeing the correct color. One of the ways you can prove this to yourself is get a really good high color rendering source that's got a very even distribution, and use it as a reference and say, okay, here's my red boxcar. How does it look like, for example, under a halogen lamp? And then compare it to what it looks like under a cool fluorescent lamp, and you'll see there's a significant difference. Now we get to LEDs, and this is another can of worms. The lighting industry is very slow to change, and this sudden influx of LEDs has caused a huge change in the lighting industry very, very quickly. It's been referred to as a wild, wild west, and part of the problem is the industry is slow to change, and part of it is that the technology is so different. So what we're dealing with LEDs, we've got three options here, and we're going to ignore the top right one for now. The one that's top right is a color mix, color changing RGB tool. So it's basically 3 LED chips on a single package. Now this is what I'm using on my layout, so you'll see the impact of that later on. But essentially we have a red, a green, and a blue LED, and they are in a single package, and we can control those 3 colors separately. If we look down, where I really want you to look is the lower left, where we have the cool white LED. Now, first thing I want to point out, the term cool white. Everyone knows what that means. After the length of time I've spent in the lighting industry, I can look at a fluorescent lamp and know right away what the color of the light is, whether it's a cool white or warm white or a neutral. And that's because the cool white lamp is 4100 Kelvin. It doesn't matter who makes it. It doesn't matter where it comes from. It's always the same. With LEDs, it's changing all that. If you look at this particular LED, it's called a cool white, but it's 5600 Kelvin. Now your eye can see the difference of 50 Kelvin. So 4100 to 5600 is a huge change. And this will appear, this particular LED will appear much, much cooler, much bluer than the cool white that you're used to. So when you're dealing with LEDs, a word of warning, don't believe the words. You will find that the names that they give lights, they have all kinds of names like bright white, soft white, golden white. None of those mean anything. The only thing that really means anything is the actual Kelvin value. The other thing that's interesting about this graph is you'll see the dotted line. The dotted line represents V lambda, and that is where your eye is sensitive. So you'll notice that the cool white LED here is particularly unsuited to what our eyes see. It's not producing light in the part of the spectrum where our eyes are sensitive. If you look over to the right, you'll see the so-called warm white, which is 3250 Kelvin. You'll see that it much more closely resembles where our eyes are sensitive. So the one on the right is going to give you much more light output to your perception. It's going to perceive it as a much brighter light source, and it's also going to be much stronger at the central part of the spectrum. One more thing about this graph before we move on, and that is you'll notice that all of these have this big, big spike at the blue end of the spectrum. And that is because, time for a reality shift, there is no such thing as a white light LED. The LEDs that we purchase today and are made today that produce white light are actually blue light LEDs, and they are producing white light because of phosphors that have been added. So those of you who are using LED light sources for your locomotives, for example, you'll notice when you look at them, they're yellow. The little surface mount LED, you look at the surface of it and it's quite yellow looking. And that's because you're looking at the phosphor. So they put a golden color phosphor on the LED. It acts like a lens and it warps or changes the light output of the LED. The more phosphor goes on, the less efficient the LED, but it also gets warmer. So you can see the result on the right-hand side here. Now, what is this correlated color temperature we've been talking about? Well, basically, the color temperature of a lamp expressed in degrees Kelvin, and it represents the whiteness of the light. The higher the value, the whiter the appearance. So if you look down at the bottom of this graph, you'll see that a candle is around 1800 Kelvin. An ordinary 40-watt incandescent light bulb, if anybody remembers what those look like, that's around 2500 to 2600 Kelvin. A halogen lamp, which you may be more familiar with still, is around 3000 to 3200 Kelvin, and that's about the same as a warm white lamp. If you go up to a cool white fluorescent is around 4000. And if you look up, you'll see up the chart, you'll see that about the strongest or the highest color temperature we can produce is around 6500 to 7000 in terms of white light sources. This is nowhere near what we get outside. An outdoor north sky is in excess of 8000 Kelvin, and you wouldn't want to use that inside, believe me. I had a client who tried once. It was not a happy thing. Color rendering index is a scale that tries to describe how well an object's colors are rendered by an artificial light source. So the colors below are examined under a reference source and under the test source. And there's also another chart that uses 14 colors, which is more accurate. The less color shift, the higher the CRI. This is done by measuring the spectrum of the reflected light from these test colors and comparing them to a standard lamp. The CRI has no units to it, it's just a number. Some would argue CRI values can actually be negative. And since LEDs have come along, there's a measurement for R9, which is another color block which indicates the red output of the LEDs. And that's because LEDs do, relatively speaking, a poor job of rendering the red end of the spectrum. Unlike our incandescent lamps, which are great at red and lousy at blue, the LEDs are terrific at blue and lousy at red. So because it's difficult for them to do that, a really high color rendering LED will have a good value for R9. So in other words, it's putting out good strength at the red end of the spectrum. And just to give you a measurement in terms of what those values might look like, so a typical cool white 4100 Kelvin T8 fluorescent lamp will have a CRI of around 85, and a typical good quality LED would have a CRI of around 80. Most of the garden variety inexpensive LEDs you would find at your local home center would probably be CRIs of around 70 or less. Okay, some basics about how we see. So unfortunately, the human eye doesn't actually see light. We only see reflected light. So if you think about going to a railroad convention maybe 25 or 30 years ago, we'd be sitting around a convention room in a meeting room in a hotel, and half of us would be puffing away on cigarettes, and you'd be able to see the beam of the projector because of what you're seeing. And what you're seeing is the smoke. You're not actually seeing the light. The light is reflecting back from the smoke, and that's what you're perceiving. Why does this matter for model railroaders? Because as a guy already pointed out, I believe he had a picture of a shay. The objects we're lighting are generally black. And anybody who's painted a locomotive knows that you don't paint it flat black, because if you do, you're not going to see anything, because of course it just absorbs everything you throw at it. And that's why we use various shades of gray when we're painting locomotives, because we want to be actually able to see them. It is absolutely essential to eliminate all glare sources from the field of vision, because our eyes are extremely sensitive to glare. Oncoming high beam headlights is the standard example. What happens when that happens? You blink your eyes to get rid of that. You open your eyes again and you can't see anything. You're night blind for the next, 5 seconds or 10 seconds or 30 seconds or a minute or more if you're older, because your eye has shrunk down to accommodate the bright light, and now it has to open up again, and that takes time. So you want to eliminate all the glare sources. If you've got a situation on your railroad where you can stand looking at, say, a peninsula part of the railroad, and there's a light on the other side of the peninsula shining towards you, and you can see that light source, you have to block that off, because you will never be able to achieve good lighting effects as long as you have glare in the environment. Same thing applies to a work environment. The thing that can get me booted out of the Illuminating Engineering Society is to tell you the best way to eliminate glare is to wear a baseball cap, but you do have to wear it the right way around. In terms of contrast, in terms of the light level on the light level or illuminance on the surfaces, about 3:1 to 5:1 is the best range. And as you can tell, these are not very high ratios. So the range is fairly narrow that our eyes accommodate comfortably. And the luminance or brightness ratios, that's the brightness of the things we're looking at, is important. The comparative brightness of the surfaces is important. As an example of that, one of the things that you would think about is going out to finding an old trestle on the narrow gauge railroad and sneakily taking a knife and shaving a little piece of the wood off so you can match the color exactly. Well, that would look great when you're outside with 10,000 lux. If you put it inside with 100 lux or 500 lux, you're not going to be able to see that. It's just going to look black to you. And that's why we cheat. We're creating an image of a perception of reality, not reality. And in order to do that, we have to use some tricks. It's just the same thing as highlighting a model by dry brushing. All those things are things that we do to increase the effect of reality in our model making. And the same thing applies to light. Now let's talk briefly about efficacy. Lamp performance or efficiency is measured in lamp lumens output per watt of energy, and it's called efficacy, similar to miles per gallon. If you use the term efficacy, you can actually charge $25 an hour more as a lighting designer, because it sounds like you really know what you're talking about. It's measured in lumens per watt, And this is problematic with LED systems because the value often used in advertising is the lumens per watt at the chip level, which is essentially meaningless. If you take an LED and you put it in a pool of liquid nitrogen in a lab, you would be unbelievable amount of light you can get out of it. But if you take that same LED chip and put it into a light fixture, into a real space, everything changes. So they're very efficient, don't get me wrong, and I'm not anti-LED by any means. I've got a ton of them in my train room. But you do need to be realistic about the limitations of the technology. As most good consultants, my idea is to let our consultant make our client make informed decisions. So here's a chart of our light source versus CRI versus efficacy. And as you can see, the incandescent at the bottom of the chart, fantastic color rendering, terrible efficiency. And what we're moving towards now, obviously, is more LED. Linear fluorescence, fantastic. It's very competitive with LED still even today. So don't think you have to rush out and buy LED fixtures. It's not absolutely necessary to do that, depending on the effects you're trying to achieve. Compact fluorescence is pretty much gone. So a little bit of economics here. Here's some reality. So we take a 4-foot LED fixture, which costs about $35 and replaces a 4-foot fixture, which costs $31 with the lamps. And this is based on actual prices at Home Depot, US, and fixtures with roughly equivalent lumens and also brand name. So this is not some unknown manufacturer. This is Lithonia or an equal good North American builder. So the LED fixture has 350 fewer lumens and the CRI is 80 compared to 85 for the T8. So it's close, but not quite as good in terms of its performance. The LED fixture, however, saves 5 watts. So if you take 5 watts times $1,000 per year at 10 cents or whatever you're paying per kilowatt hour is 50 cents per year saving. So it's going to take 8 years to save enough to pay for the difference between the LED fixture and the fluorescent fixture. So it's a very small saving, but it's not as grand as you might believe. So make informed decisions. Make sure you don't go in there thinking, oh, I'm going to save a fortune by buying this fixture. No, you're not. Reality is reality. Okay, so let's take a look at some sample colors and what they would look like on some real models. So we're going to look at a 3000 Kelvin lamp. This particular one is fluorescent, but it could be LED. And this is a high CRI lamp at 85 CRI. And this is a model of the second kit that Mount Albert did. This is the brewery. And if we look at this picture, we see, well, the reds look like this is a warm lamp. And as you can see, the rust on the roof, the warm colors in the background. This is on my last layout. It was located in Toronto. And it had, this was before we did any ground foam, so there was a lot of reds in the coloring at that time. And but if you look at the green around the doors, the door frames and window frames, it's a little wishy-washy because this light has very relatively poor output at the blue end of the spectrum. So not a lot going on there. So let's take a look at something a little cooler. Let's go to the other extreme. So let's take a look at a cool white fluorescent. Or LED, and this is 4100 Kelvin. And now, my goodness, what a difference. The same building, same scene, same camera angle, same everything, but boy, oh boy, is it blue. So first of all, our backdrop looks fantastic. Our sign with the blue on the sign has really come alive, but look at the green around the doors. This really pops now, which it didn't before. Now, however, we're starting to lose all of the warm end of the spectrum, which is a cool white lamp, obviously has very little output, as we saw earlier, at the warm end of the spectrum. And as you can see, the warm colors are generally being lost. So let's try a compromise. Let's go for a neutral color and see where that gets us. Well, this is, I think, quite a bit better because it gives us sort of the best of both worlds. We haven't lost the greens. The greens are pretty good. The blue is not bad. The backdrop color is okay. But we've got the rust back on our roof. We can see the colors in the stones quite well. Everything's being rendered pretty well. However, there's one problem here. With all of the ones we've looked at so far, this is just using a diffuse light source. Fluorescent lamps and most LED sources are generally considered, if they're shielded, generally considered diffuse light sources as opposed to point sources. So when you look at this, if this was the outdoor world, as we're trying to convince ourselves, this would be a cloudy day. There are no hard shadows anywhere. So this would be an overcast day. I think it was Guy who talked about the color of the sky, having to change the color of the sky. Okay, so let's take a look at what happens if we add some accent light to this. Now we're going to add either 20-watt halogen or 6-watt LED accent light. Now all of a sudden we have a lot more three-dimensional quality to the model because all of the shadows are now there. The other reason this works better for us is that now we have a time of day. We know it's judging by the shadows, the sun is up and to our left. It's not directly overhead. It's not down on the horizon. So it may be, I don't know, 9 o'clock or 10 o'clock in the morning, or maybe 3 or 4 o'clock or 5 o'clock in the afternoon. So we have a placement. So we have a geographic placement. We also have now a placement in space. So it's space and time. So it adds to the overall reality. The other thing that we've added is we've added a hell of a lot more contrast in our model. So remember we talked about contrast ratios and how important they are. Now those stones really rock because we have got really clear shadow lines between the stones. We've got shadow lines underneath even the sills on the windows are giving us shadows. We've got a very interesting shadow of the ladder on the roof of the front of the building. So there's all kinds of things happening now which bring a whole lot more dimension to our modeling. And this is why I'm a big fan of using accent lighting. This is something I learned from my museum lighting, is that you really need to see the model in 3 dimensions. And doing it this way really helps you achieve that. You can't achieve this with just diffuse light sources. So let's look at the before and after. Here it is without, and here it is with. So now I'm going to talk about what happens when we add some color to these scenes using some LED strips. So these are readily available LED strips, which are RGB, which is red, green, blue, basically, which permit adjusting color to the time of day. The term for this in the lighting world is called diurnal. So we're actually achieving a entire day effect by altering the color of the light. So here's a sequence. This requires a separate system of LED color changing strip and a controller, and it can be costly. Now let's take a look and see what that looks like. So here's a scene on my present layout. This is a wharf scene. I've temporarily put this little building on so I can give something 3-dimensional and right up front that you can see, and also it has the advantage of having some lighting in it. And a character and a locomotive, and the background is a temporary background I put in place for this photograph, and it's a trackside sceneries background. So what we've got here is we've got a dawn effect. We've got some yellow light on, we've got some white light on. It's been dimmed, and we're gradually going to bring this up until day. So now we have the day effect. And as you can see, it's pretty much all white light. We've got some focus light because you can see the shadow line on the front of the building. Now we slide into the sunset effect, and you can see we've got mostly the red LED on. The building lighting has come on, and there is some white light in this sunset. As you can see, there's some shadowing on the front, just a very small amount. And now we go to our night effect, which basically is all the blue colored light on full, and there's also a little white light in here in order to give a moonlight type of effect and make it so that it's not absolutely invisible, because the light level here at the night effect is roughly 1/10 of what the day effect is. So it's a lot darker. This is where building lighting really comes in handy. And when we can go back to the dawn effect, so you can see the difference. The building light's gone out, obviously, and everything's starting to come to life. And it'll go back to the day. Okay, now how do we achieve that? So we got three things going on. We've got Sylvania Mosaic LED dimmable color strip light with 3 color LEDs. This is available, as product is available online, and also Home Depot, I believe, carries this in the US. I've got a T8 fluorescent dimming ambient light to give me basically my white light, my work light, and also my overall lighting for my daytime effect. I used T8 fluorescent at the time. I started doing this layout 8 years ago. So at that time, there really wasn't a white LED that was producing enough light to replace a T8. There is today. But back then I didn't have a lot of choice. So I had to use the dimming fluorescent. Dimming fluorescent is possible. It's expensive because the ballasts are expensive. Well, what can I say? I know a guy. And then our focus light is a 7-watt LED accent light, which we'll look at in the next slide. And then we're using a control system that using a programmable lighting controller, which we'll look at in a couple of slides. So here's a really low-cost LED accent light. Lighting doesn't have to be expensive. So we have a standard octal box, which is less than $1. We have an RAB or red dot lamp holder, which is less than $5. And we have a Sylvania lamp. I've given you the part number. It's an LED par 16 lamp with 36-degree flood, 6 watts, 3000 Kelvin, CRI 82. It's about $10. Now I know right away somebody's going online and going, oh, I'm sure I can get those cheaper. Unfortunately, in lighting as in life, you basically get what you pay for. This is a high-end lamp. It is designed, it's in the Sylvania Ultra series. It's designed for high-end retail. It's excellent color rendering, and it's got, it's very consistent from lamp to lamp. It has a very soft edge beam, which is very desirable because you don't want a hard edge. That doesn't really happen in the sunshine. You don't get round pools of light. I've seen that done on layouts. It's very unrealistic. You need something soft that blends in, and this is what that lamp does. And 3000 Kelvin, so it's warm. And the 36-degree flood is about right for most model railroads I've found. Usually our throw distance, my throw distances are less than 4 feet. If you've got an 8-foot ceiling and your bench works at 4 feet, then you've got a 4-foot throw distance. So you don't really need more than that. You don't need a real tight spot because you're just going to have a little pool of light about, very small, net 8 or 9 inches in diameter, less than a foot. You need something that's more even and more spread out a bit. This particular fixture, I've got about 20 of these scattered around my layout, and it's useful for valence or drop ceiling applications where the appearance of the fixture is not relevant. You're not going to use this in your living room, but if you've got it hidden behind a valence or above a drop ceiling, it's going to perform really well for you. And here's the effects controller. It looks expensive and is. It's about the price of a brass locomotive. And that's basically the way I rationalize it. I could buy another brass locomotive, or I could have a lighting controller that enables me to create a diurnal effect on my layout, completely automated. And I can control it myself. I've got a wireless controller for it where I can control it from anywhere in the train room. I can set it on a sequence where I hit a button and it goes through the whole day-night sequence automatically. So it's very sophisticated and does everything I need. This takes a 4-gang box to install it. Okay, so now some first principles of design. First of all, light is a model too. We talked a little bit about this before. So outside noonday sun is around 10,000 lux or 1,000 foot candles. And it's about 6,000 Kelvin or more in terms of color temperature. And you're not going to do that inside. A, you couldn't afford it, and B, everything would fade in about 8 minutes. So the illuminance inside typically is on a layout is going to be somewhere between 500 and 1,000 lux, which is 50 to 100 foot candles. And it's going to be about 3,000 to 4,500 Kelvin. The other thing we're looking at is what is our time of day? So this is when you're doing your design and when you're thinking about how you're going to light your railroad, you want to think about, what am I modeling? What effect am I trying to achieve? So time of day is important. Early and late in the day is going to be warmer color temperatures. Midday is going to be cooler color temperatures, 3,500 to 4,500. I chickened out and I solved this problem by having it possible to do anything. So I can make it any time of day I want. How much light do I need? So this is critical to determine the illuminance, lux or foot candles required. You need to find out how much light do I need. So there's two tasks involved here. There's the construction phase, where you usually require higher illuminance than viewing or operations. Portable lighting is very useful for this because, generally speaking, after you finish the construction phase, you really don't need that light level again. Once again, I solved this by dimming, so I can bring my lights up to full. I've got over 1,000 lux, over 100 foot candles with everything on full. Once I get into no more construction, which would be a wonderful thing, we can crank everything down. The other issue is the aging eye. I would take a wild guess that there's not a whole lot of people younger than 50 on the webinar today. Person age 60 requires 3 times the illuminance as a person who is 20, and that's without other vision problems. So all of us old guys, I'm 71, we need a lot more light in order to see the same as our grandkids or children. So we need to allow for that on our models. I would suggest a minimum illuminance, and this is an absolute minimum of 50 foot candles or 500 lux on the railroad. And that doesn't include accent lighting. My layout daytime effect illuminance is over 1,000 lux, 100 foot candles. And all of my friends who visited my layout have said, wow, I can really see it. It's great. You know, they're not squinting, except when I do the night effect and they're all squinting. If you want to measure the light you've got, there's several light meter apps that work with smartphones. They're certainly accurate enough. They're not scientific instruments, but they're accurate enough for this purpose. The one I use is the Lux Light Meter Pro, but as I say, there's a ton of them out there. You want to use the color of light you're using to set the scene. So the time of year, summer and fall, you're going to be warmer colors. Winter and spring are going to be cooler colors. A geographic location, mountain country, Colorado, also called Big Sky Country. Anybody who's been there, and I imagine many of us have, definitely tends towards cooler color temperatures. Any of you who were in Minneapolis last year probably would have seen our Dolores modules, which won first prize in the modules contest. We used 4,100 Kelvin because it's Colorado, and that was the effect we were looking for. Is that coolness in the colors that are typical of Colorado. If you were modeling West Side or EBT in Pennsylvania, you would want a warmer color temperature typically. In terms of CRI, you want to shoot for the highest CRI you can afford. Use some point sources. I think I've demonstrated the value of using point sources to create accent light and really pick up your key items in your layout. You're going to have parts of your layout which are transitional, and you got parts of your layout where the wow factor is, just like in a museum display. Museum display, one of the questions we always asked curators was, what's the most important object in this case, or what's the most important object in this exhibition? And once you found out what that is, either historically or archaeologically, then you would focus so that when people came to that, it was the wow factor. People go, wow. And everyone has that on their layout. They have a building, or they have a scene that they've created, or a wonderful piece of scenery. And that's the wow factor. You want people to really see that. So you draw their attention to it. You use the lighting to bring people's attention to where you want it. Fluorescent or diffuse LED, in my opinion, is just too flat. Light your layout for building and operating, light separately for photography. IKEA has great clamp lamps. This is less of an issue with digital cameras, but as I believe it was Guy pointed out earlier, if you're lighting something like a Shay or something, a very dark locomotive against a light background, you're probably gonna have to bring in some auxiliary light to make that thing render properly in a photograph. Or get in there and Photoshop and have fun. I'm going to spend a little bit of time on fading because this is a question that comes up a lot. People are often asking me about this. So how do I resolve this? And any light causes fading over time. It's not just the UV component. UV is the worst. It's the most deleterious part of the light spectrum in terms of producing, or energy spectrum, in terms of producing fading. but everything will fade over time. It's a function of the quantity of light, the time of exposure. In the museum world, they call this lux hours. The light source type, how much UV is being produced by the light source, and the sensitivity of the objects. Now, for our model railroaders, for most of the paints we're using on our rolling stock and our structures, it's not a huge problem. The most sensitive object probably in the layout are scenery items. So in particular, ground foam is particularly prone to fading, and anything that's a natural material. You'll probably find, as a guy was talking about, and I've done this myself, using natural materials for scenery, particularly sticks and logs and things like that on the layout. They will fade over time. You'll find that's what happens. It's just nature doing its thing. One thing you can do, just as an aside, one thing you can do if you want an interesting experiment is take some pieces of stripwood that you're doing for building a trestle or some small structure, and do your usual graining and staining and all that stuff, and then take it outside and leave it on a nice sunny day and leave it outside for a day. You get some really interesting effects that way. So to minimize fading, you want to keep the light levels reasonable and turn them off when not needed. Basically, don't have them on if you're not there running trains. Fluorescent lights will cause the most fading. Newer style T5 and T8 fluorescent lamps are the best. Avoid old style T12 lamps, especially 8-foot types. Actually, a little health warning here. If you have any 8-foot T12 lamps in your garage or workshop or anywhere like that, get rid of them today. They've been banned by NIOSH because they have such high UV output. It's really deleterious to your health. So you get rid of those puppies, they're dangerous. There is no UV with LED sources, so that's a real bonus. UV filters are available for layouts with long exposure hours like museum displays. They're probably not worth the cost for home layouts. There'll still be some fading even with the filters. And without a UV meter, you can't tell if the filters are still effective. In the museum world, the conservators go around to all the displays on a regular basis with UV meters, light meters. They're measuring humidity. They're doing all that stuff. They're doing their due diligence. Most model railroaders aren't quite that anal yet. So one of the interesting aspects of lighting design, and it's something that suits me perfectly because there's no real right or wrong way. There are a number of choices, and they all offer different compromises and different effects. So you need to decide, how much do I want to spend? What do I want to achieve? And then make your decisions based on that. Human vision is dependent on perception, and perception is individual. So what looks like right to you may not look right to the next guy. So don't let that bother you. We all have separate, our own independent way of viewing. So it's very, very subjective. 10% of the male population is functionally blind. So if we have 180 people on, that means we've got 18 guys that are functionally colorblind. So Pete's waving his hand there. There's some tests you can have to find out whether you are and how much and what part of the spectrum. It can help you a little bit. Any decent optometrist should be able to do that. If you want a real thorough test, you need to see an ophthalmologist. There's some online tests that are not very good. They just give you sort of a yes or no, and then you need to drill down. Make sure you test before you buy, because as I say, it is very, very, very personal. I had a friend who did a very beautiful layout in Durango years ago, and I did the lighting design for him. And I suggested a very high-end, high-quality, high output, and a good color rendering lamp. And he found a much cheaper one, half price. He was very proud of the fact that he found these half-price lamps. And he discovered after a while that he was having a lot of failures, and the color was changing over time, which of course will happen. Even with the LED lights, the color will change over time because the phosphors degrade because of the heat. And so make sure you test before you buy, make sure you're happy before you spring for, 30 or 40 or even 10 or 12 lamps, because you want to make sure you're going to like it. So I'm going to look at a design approach for a couple of standard type layouts. We want to use diffuse ambient light using low energy and low heat sources such as fluorescent or diffuse LED. We want to use focus spotlights or accent lights to provide shadows and better 3D modeling using incandescent or accent LED. For double deck layouts, space is the obvious challenge. You can use undercounter halogen or puck lights when space is really limited. These things are down to ½ an inch or less in height. So very, very, very low profile. So it is possible to do this. There's some very nice little LED strip lighting, which they sell at places like IKEA, which is designed for putting under the counter, and extremely low profile. A lot of these are plug and play. You usually pay a little bit more for plug and play, but that's really handy for a railroad because you can just keep plugging units on until you run out of energy. They'll tell you how many you can put together. So here's a couple of diagrams showing a typical section. The top left drawing shows a valence with a piece of blocking in. The blocking is basically there just so you have something to mount the valence to or fasten it to. And then next to that is showing a junction box with a typical accent light. If you look at to the right, you'll see the same detail except with a fluorescent lamp. That could also be an LED. The height is to suit because it depends on your ceiling height. So you really have to adapt that, figure out that height that makes sure that you can see the backdrop, but you don't see the fixture. And the depth away from the wall. So if we take our overall depth away from the wall as X, then the distance for the valence will need to be X plus or minus 6 inches. It's not that critical. It's surprising how well the diffuse part of our lighting will diffuse it out and spread it around. However, there is one proviso, and that is that if you have structures or track really close to the front edge of the layout, then they will be in silhouette if they are closer to the viewer than the light fixture. So I would tend to have my valence maybe 3 to 6 inches further away from the wall than the front edge of the layout. And that means you're going to be well illuminated right to the edge of the layout. What you want to eliminate really is somebody standing at the front edge of the layout and having their shadow appearing on the layout. And that's when the fixture is way too far away. I've seen guys try to economize by putting a track down the middle of an aisle and lighting a layout on both sides. And the downside of that is that if it's too far away from the edge of the layout, what will happen is if you're standing in front of the layout looking at it, what you're looking at is your shadow. And you definitely want to avoid that because nothing ruins the effect more than having your shadow in the middle of your universe. The same thing applies to trees. You need to be careful of trees close to the backdrop so that you don't have a shadow on the backdrop. In terms of the workspace, you really want to model onto the same lights as on the layout, especially when painting or weathering. And that wraps it up. I've got a couple of thank yous here to do. My wife did the photography for me. She's a gifted amateur photographer. And my friend Roger Malnowski, who built the Mount Albert pilot model. And of course, the St. Louis Committee for making these webinars possible. There's one thing I forgot to mention. If you are interested, tune in next week for these clinics. After the clinics next week, you'll be getting a video tour of the Fast Track shop. So I think a lot of you will find that quite interesting because you'll see some of the equipment at work. And it's quite entertaining. So, questions?
Thank you, Gerry. If you guys can hear me.
Yep.
Yeah, I got a few questions, which is good. I'll try and go through them. There's a few more coming in. So I'll just do them in the order I actually saw them, Gerry. So from S. Hollenbach, he says, we have some modules with a skyboard, mostly painted light blue. However, more recent modules with city scenes have no backdrops, so they can be seen from both sides. Looking for a way to light them, and as an additional question, does the backdrop color have a significant effect on lighting?
Okay, well, that's a complex question, but we'll try to see what we can do.
Yep.
Yes, there are ways to light that. The way we did our Dolores modules is we used a fixture from a company called Lightline. That's L-I-T-E-L-I-N-E, which is a very shallow fixtures designed to be used as a task light under a counter. And they come in lengths from 9 inches up to about 54 inches. They can be plugged together. They have cables for connecting them together, and they are available in both fluorescent, T5 fluorescent, and also in LED versions. So it's a very good option for lighting modular layout where you have a limited space. In terms of the color of the light on the backdrop, yes, the color of the backdrop will have an impact because that color will be reflected back into the room and, of course, reflected back into the eyes of the viewers, right? So it's yeah, tricky. Like I say, get one, try it. Make sure you like it before you do the whole thing. We did the Dolores modules that we did a few years back. They're 56 feet of that. And we did all of that was done with those Lightline fixtures, and we've been very happy with the look of that.
Okay, well, thanks,
did I cover all of that? Did I cover all of that?
I think so.
Okay.
So there's several questions in there, which is fair enough. And so the next one is from Mike Conda. It says, how can one use accent light in the yard area? Concerned about multiple accent lights giving multiple shadows. You know, we see that in movies a lot, right? Particularly in the old Star Trek stuff. There's lots of random shadows around. So any way to intelligently avoid having those multiple shadows?
Well, the easy thing to do is to do what Star Trek did and pretend that the planet had 2 moons, or 2 suns rather. That solves that whole problem.
Okay.
So
next question. No, I've got carry on.
Change your layout. No, what I've done in my layout, for example, I'm pretty selective about accent lighting, and I want to keep them fairly far apart. So my accent lights are typically about 5 feet apart. They've got a very soft edge, so they don't overlap one to the other. That gets around the problem of multiple shadows. Typically what I would do on a yard is I would light perhaps a turntable engine house combination. There's lots going on. It's very busy. There's interesting structure. There's all kinds of stuff going on. If you've got a row of tracks with a bunch of boxcars in it, that's probably not so visually exciting, and you probably don't need to put accent lighting there. Focus the light where you need it. Don't feel like you have to put accent light every 3 inches. It's not necessary or even desirable. I did an art gallery years ago, and the reason they hired me was they were getting complaints from people about the lighting. And what they'd done is they'd taken a spotlight and put it on every single fixture, every single art piece. And your impression after you walk through the gallery, and this was a big gallery, was that they had a lot of art pieces. But there really wasn't anything that stood out because everything was exactly the same. It was all lit exactly the same. So you really want to have a little variety as you go around the layout.
Okay, thanks, Gerry. So T. Mana asked, how many electrical circuits are used for the lighting design that you built? I assume he's referring to your home layout. 15 amp, 20 amp? Because it seems like you had a lot of lighting, so I think he's trying to understand how you, from electrician's point of view, how you set that up.
Right, good question. Yes, I'm using a single circuit, a 15 amp circuit, and that covers all my lighting, and I've actually got some room there. So, and I've got, as I said, I've got, I think I have 12, no, that's not correct. I've got 15 4-foot fixtures. They're not butt mounted, there's space in between them. And I've got 150 feet of LED, and I've got 20 6-watt or 7-watt LED spotlights. And I've still got ample space in there. I'm not using my 80% of my 15 amps, so I'm in good shape.
Cool. Okay. From Dean Smith, who's he? Now I remember Dean Smith. Okay. Where do soft white, fluorescent, and incandescent lights fit into this spectrum? So where does soft white, fluorescent, incandescent fit in?
Okay, well, soft white is, once again, one of those terms that isn't really a term. It's basically a name that was used by marketers for incandescent lamps that were diffuse. So they called it soft as opposed to harsh, which would be an uncoated lamp. So it was just another way of marketing diffuse lamps. So I wouldn't worry too much about the nomenclature there.
By the way, you asked, does anyone have a 40-watt a 40-watt incandescent bulb. I actually have one right behind my desk here because I'm doing a Zoom play on Shakespeare, so I need some backlighting. So I actually have a 40-watt bulb right behind my desk.
That'll do the job. Very nice.
From David Emery, any suggestions or recommendations on powering LED light strips? And he also adds as an addendum, it's also worth noting that cataracts will change color perception long before you notice the deterioration. My speech is going long before you notice the deterioration in your vision.
Yeah, that deteriorate word really gets a lot of people.
It's not Shakespearean. So.
That's a Shakespearean thing. Yeah. Well, that was probably not a word that Shakespeare used a lot. For powering LED light strips, I'm using a driver for my LED strips that was provided by the manufacturer. It's always best to stay within the family in terms of drivers. The relationship between the drivers and the LEDs is critical for the success of an LED system. So I'd be cautious about using third-party drivers. If we're using Sylvania LEDs, I'd be using a Sylvania driver. Because that relationship is very tricky electrically, especially if you're dimming them. And it's a really good point about the cataracts. Yes, I have a number of friends that have had that experience, and you're absolutely right. You will notice color changes before it becomes a problem.
So there's 2 more questions, but let me ask one. Gerry just came up. I was putting some LED lights actually outside around a telescope in my front yard and some red LED lights around it so I don't walk into things at night. The word driver I find confusing. Is it just a fancy name for a power supply? And if so, does it have a specific current and voltage requirement? I know you mentioned that using specific drivers. So is a driver anything fancy, or is it just really a power supply?
It's both. Okay. It is a power supply. There's no question. LEDs run on DC. And most of our line voltage is AC, so we have to be able to change it to DC. And also most of our LEDs, typically voltage drop across an LED is less than 3 volts, so it's relatively low voltage, so we have to control that. But that's not the hard part. The hard part really is the controlling the current through the LEDs, and it depends entirely on how many LEDs we have. So if we have a strip with 20 LEDs on it, that's one thing. If we add another strip and there's now 40 LEDs, that's a different thing. So the manufacturers who make the units that you've put together that you can add units to always have a limit, and that limit is determined by the driver. They'll say, okay, you know, we'll let you can have 70 feet of this stuff, but if you go to 80 feet, you're going to have a problem. And their problems manifest themselves in failures and also in color shifting.
Okay.
Yeah.
Okay, I'll dig into that a bit more for me because I'm interested. So 2 more questions that I can see from Tom O'Hara. If someone is planning a new layout but is planning to transfer a lot of models from an old layout, do you have any suggestions on how to figure out the new lighting so that the room blends in with the old models? I think it's looking for actually no color shift if you build a new layout with different lighting, so stuff looks the same.
I would look at what the lighting was on the old layout, and if you were happy with that, I would try to reproduce that same color on the new layout. The biggest single element is going to be the color temperature, and color rendering will be a secondary item as well. So if you had a layout that was lit however it was lit, maybe it was warm white fluorescent, then I would be looking for 3000 Kelvin LED because that's going to give you the same spectrum. And so you're not going to be altering the look of the models so much doing that.
I guess that would be an interesting question if you're going from old technology to new technology, going from a mixture of, I don't know, fluorescent and incandescent to LED. It's probably not an easy question, but it's still about the color balance, right?
Absolutely, yeah. Yep. Yeah, it won't be exactly the same. And as we've said, you know, a lot of these, there are a lot of variables, especially in the LED world. There's a huge number of variables in performance and also in color performance. So yeah, color reproduction. So yeah, like I said, buy one, try it. If you find something you like, go crazy. Yeah.
And the final one from Frank DeSimone. Please compare daylight LED strip with cool and warm LED strip. I think it's a question of definitions, right? So
yeah,
daylight LED, yeah.
I think, as I mentioned, you have to be really careful with these terms when you come to LEDs. So when an LED manufacturer says daylight, what exactly does he mean? I don't know. I can't tell you that, and I'm a lighting designer. So I would be looking for the go online, find that manufacturer's specifications for the product, and find out what is the color temperature. The color temperature of the product is actually required by law to be on the label of any lighting product sold in North America. Unfortunately, there's an awful lot of product that comes in gray market, and that information is missing somehow. So it is buyer beware. And the same with cool white and warm white. These are terms that have changed in meaning in terms of what they used to mean. So there used to be an engineering definition of what a cool white was, and everybody stuck to that same definition. So they were always 4100K. Now cool white can mean almost anything. Just as an example of that, DOE in the US did a fantastic research product where they bought LED product on the open market and compared it. And they compared it to its own specifications in addition to comparing from product to product. And the definition of a replacement for an A-lamp, a 40-watt A-lamp that you just held up, is supposed to be about 2800 Kelvin. And the LED products that were supposed to match that varied from 2500 Kelvin to 7000 Kelvin.
Whoa.
So the name warm white and the name cool white really means absolutely nothing today, because people are getting away with murder. So you really need to try it, buy it, try it. If you like it, go for it. If you don't like it, walk away.
Yeah, thanks, Gerry. That's it. And I know from my experience, if you look on eBay, for example, where stuff is probably coming directly from, wherever, China or somewhere, yeah, it probably doesn't have that labeling on because it's kind of gray might be the word. So thanks, Gerry. So Russ, back to you. I think we're done with the questions. Actually, one more snuck in. Mike Conda asked, how do you calculate flux from lumen data from a fixture? How fast does distance reduce flux?
Well, I have a 2-hour class on how to do that. It's part of the lighting calculation, but the short answer is the inverse square law, the amount of light divided by the distance squared.
Okay. I remember how that works. Okay.
All right, everybody.
Thank you. I'll go back to Russ. Thanks.
Great. Thank you, Gerry. I realize now I've got to go up to my train room and make some adjustments. Thank you again for our presenters. Outstanding work. And I think you all realize what we've put together are some great presentations. We have 2 layout tours this afternoon. One is Chuck Graham, Denver Rio Grande 4th Division, and Axel Kramer, which is an ON30 freelance, or ON3 rather, freelance layout. So those will appear in sequence this afternoon after we get started.